Yeah, my name's Jason. Yeah, I'm just representing
And your surname?
Trevers.
Thank you.
I originally put down for an hour, and I notice I'm starting 10 minutes early. Does that give me allocation for a few extra minutes, or I'm still...
It will, as long as we're finished by 12:30, that's fine.
Yep,
Thank you.
cool. Just grab water.
When I say finished by 12:30, that includes questions. Thank you.
Cool. Yeah, if you can give me a card at 10 minutes to go, then I'll play my video.
You'll get one of these at 5 minutes to go.
Oh,
Thank you.
I'll just start a stopwatch for myself so I can keep track. Well, hello panel. Yeah, my name's Jason. I've been presenting to you a few times before. I think this is my third time now. I've become deeply disappointed at the process and the outcome of the final draft of the inquiry. I feel that the inquiry has no integrity, and as an independent inquiry, it was initially portrayed as. It has been a waste of time and money. I've personally invested a great deal into gathering information for this inquiry and presenting before you. I've been commended for my presentations, but it has amounted to nothing. The Chief Minister, Michael Gunner, appointed the independent scientific panel to inquire into the environmental impacts and risks associated with hydraulic fracturing. It is your job to assess the risks with regard to the most relevant, current and available scientific information. Fracking has many risks and potential things that can go catastrophically wrong. Not a single unconventional gas field has completed its life cycle of the gas field. It is a new experimental technology. Already there is evidence of countless incidences where the environment has been detrimentally affected, habitats destroyed, surface and groundwater contaminated, drinking water contaminated, just to name a few. I've personally spent many hours to the early hours of the morning researching fracking to present my findings before you. I do not have time to look at all the issues, so I'll just look at one which I think is a pivotal point: well integrity. In my first presentation, I presented to you the fact that 7% of new wells leak, and as wells age, that percentage increases to 30 to 50% at the end of the well's life. I provided a video of Dr. Ingraffa, a world-renowned authority and respected scientist on the subject of fracking, and other documentation to back up my claim. I was shocked to read your report where you printed APIA's figures of 0.004%, 1 in 20,000 well integrity failures. I challenged this in my next presentation to you, providing peer-reviewed scientific papers. One of them titled Implications for Shale and Unconventional Reserve, was a title, Oil and Gas Well and Their Integrity, Implications for Shale and Unconventional Resource Exploration. This peer-reviewed article was written by 9 scientists from 5 different universities or institutions, compiled from 25 reliable data sets from around the world. Its conclusion sort of showed there was a large variability, but between 2% and 5% of instances were well integrity failures over the 4 million relative of the reliable data sets. APIA's data must have missed this exclusive study. Another well-documented fact is that the rate of well failure increases with age. Steel rust and scent degrades. It's an unsolved problem. 30 to 50% of wells that are fracked at the end of the life are leaking. When a well is capped or plugged, it will continue to leak on the outside layer where degradation continues to rapidly, and eventually the steel and cement will decay completely. Dr. Matthew Currell, Senior Lecturer, Environment Engineer, RMIT University, also responded to your interterm report. And where was that? He said, there is clearly a large discrepancy in the rates of well integrity failures reported in academic literature, e.g. in GRAPHA, ETAL 2014, and Jackson studies cited in the interim report, literature produced by the oil company and gas industry APIA. The inquiry's interterm report quotes well failure rates ranging as high as 6% based on academic sources to as low as 0.004% according to petroleum and gas industry sources. The reasons for this discrepancy should be thoroughly investigated and resolved by the inquiry prior to any judgment about risk levels. This part of APIA's information that I used to derive this figure came from Society of Petroleum Engineers. In a video I'll show you later, the Society of Petroleum Engineers also has documentation quoting 5% well failure rate. So the same organisation is quoting very different figures depending on who they want to target. Dr. Matthew Curran said that the EPA figures derived from an article from the Society of Petroleum Engineers. The article was not available to the public or academics, but did not stack up against a multitude of peer-reviewed articles and worldwide datasets. To get their low, unrealistic data, APA used a hand-selected data from Groundwater Protection Council 2011 study of onshore conventional gas fields, not unconventional gas fields. Quoting from Kim Kieran ETAL 2017 review of well integrity issues, it is clear that unconventional oil and gas resources present particular challenges with respect to maintaining well integrity. The oil and gas industry have spent millions of dollars and decades trying to improve well integrity issues and have been unable to improve the technology significantly to reduce well barrier failure. So they have resorted to spending millions of dollars intentionally misleading the public to make people believe that their extra layers of steel and cement will keep the hydrocarbons and toxic chemicals separate from our water and atmosphere forever. The panel have misled the public by ignoring scientific evidence and data and facts presented and running with the gas industry's misleading campaign. The panel has been presented with large amounts of information and has shown prejudice towards APIA and their fantasy-full, delusional, unrealistic statistics of 0.004%. By printing it in their interterm report, when challenged by myself, Dr. Matthew Carroll, and others to get to the bottom of the 1,000-fold discrepancy in statistics from the EPA, the multiple peer-reviewed articles and worldwide datasets, the independent panel charged with the responsibility of assessing the risks and report to the public decide to sidestep this integral issue and appoint the Commonwealth Scientific Industrial Research Organisation. Wikipedia say that the chief role of CSIRO is to improve the economic and social performance of industry. CSIRO in recent times has had a $115 million budget cut. It is not about to produce information statistics that are contrary to the will of the Commonwealth and the economy. So it's no surprise that the CSIRO statistics do not match worldwide data sets. 0.01% well failure, 1 in 1,000, well integrity issues compared to 5%, 1 in 20, is a 50-fold differential. Much better than 1,000-fold, but still nowhere close. CSIRO also failed to acknowledge a well-documented problem in the industry, that well failure rate increases as they age. They degrade over time. CSIRO found some study that seemed to ascertain or suggest that cement should remain intact for 1,000 years. I'm sure the statistics of the CSIRO did not show the collapsed well at the Dingo gas field 40 k's south of town, or the falsely fracked well at Lucy Creek. Due to the fact that we have a completely unregulated industry at the moment, they can basically pull out whatever figures they want. So it's not surprising that they got close to 0% well failure rates. As members of the panel, you'll be aware the process and construction of a well. You would know how impossible it is to drill a well without contaminating local aquifers. Drilling the well contaminates the local aquifer with the local soil and contaminates with the drilling mud, which is pumped at pressure in large quantities into the aquifers as the initial well is drilled. Drilling mud contains chemicals toxic to human and animal health. So yeah, before all the concrete and steel can be put in there, you're drilling straight into the aquifers. More layers of steel and cement means larger drill holes, which means more contamination to the aquifer. Multi-wells compound the local contamination aquifers tenfold. Multiple layers of steel and cement are added as a protection around the shallow aquifer, but often the deeper aquifers are not protected by additional layers of cement and steel. Not only are these often multiple layers of aquifers under the surface, there are often also multiple layers of shale deposits. Then the target layers containing pressurized hydrocarbon gases. While the production casing is being drilled, hydrocarbons have free access to lower unprotected aquifers. CSIRO did a $6.25 million study in the Greater Artesian Basin, GABWRA, taking 2.5 years to complete. Their finding demonstrates that groundwater has a greater potential to move vertically between aquifers than first thought. It cannot be assumed that deeper aquifers and superficial aquifers are not connected. When the cement is actually put down into the well, it has to travel 3 or 4 kilometres down and maybe another 3 or 4 kilometres across, where it's pumped back, trying to seal up to the surface, back up to the top. This is where you want your strongest cement and your strongest fixing, because this is what's protecting the water layers above. But this is the poorest quality cement. It is pumped through the drillings of the open it picks up debris from the hydrocarbons, the oily-based substances, and multiple layers of chemicals or particles as it goes up there. So your poorest quality of cement is where you want the strongest bond to last for eternity. When it gets to the shallow shale layers, it's met as a liquid cement with high pressure gas, which deviate and reduce the bond. That high pressurized gas can actually add to bubble sort of effects going further up the tube and column into where you need the strongest bond of cement. There's a judgment made by the people doing the cementing, because it costs a lot to run a drill rig, and they don't want hours and hours going by waiting for the cement to go off. So it takes a couple of hours, but it's a fine line. And if they get it wrong the other side, you get lockup, where the cement doesn't get all the way up to where you want it to go, and you have open annuluses going up to the water aquifers. In a well, the steel and cement are exposed to large amount of corrosive chemicals. Truckloads of hydrochloric acid are pumped into the well during a fracking, and they're pumped in pure, not diluted. There is a high salt content in the target shale and the product water that flows through the steel pipe for decades. In a saline environment, steel rusts and corrodes, calcifies, and cement loses strength and integrity and turns to powder. I'd just like to introduce my first video, and this is one I tried to. I've presented the panel a few times now and tried to play last time. This is Dr. Ingraffa. He's been working for 4 decades within the industry.
Is this the same video that you presented last time?
I tried to, but it didn't work.
Ah, okay, thank you. Yep.
Yeah.
No, good, excellent.
Is not shown. And it doesn't, I want to make sure you understand this, because there are millions of dollars being spent by the oil and gas industry on television ads and on newspaper ads right now that want you to believe that 4 layers of steel and 4 layers of cement are better than 3 layers of steel and 3 layers of cement. And 3 layers of steel and 3 layers of cement are better than 2 layers of steel and 2 layers of cement. And they want you to know that they're now using up to 4 or 5 or 6 layers of steel and cement. Doesn't make a damn bit of difference. There's always an outermost layer. There's always an outermost layer. I don't care how many you have, there's always a contact layer between the cement and the rock. And that's the contact, that bond. They can't detect it, they can't measure it, they can't observe it. There are techniques for figuring out whether the cement is in contact with the casing, with the steel casing. Lots of good technology to tell them that. But what they can't tell is whether there's good bond between the outside of the cement and the inside of the rock. And by the way, it's not just one kind of rock. You might be 7,000 or 8,000 feet down. There could be hundreds of different kinds of rock, each of which has its own chemistry, its own coefficient of friction, its own bonding chemistry with the cement. And you've got one kind of cement that you want to bond to all those different kinds of rock. So it doesn't make any difference. That is disingenuous on the part of the industry to say, we're now using more steel and more casing to give you more protection. Totally irrelevant. Doesn't make a damn bit of difference. How do I know that the industry knows this? Because the industry publishes its own statistics. It has its own culture. It has its own journals. It has its own reviewers, its own editors. So I know how much on a Saturday morning you want to spend time looking at bar charts, but you're going to spend some time on bar charts. This one is from Schlumberger in their journal. They went out and they surveyed 45,000 offshore oil and gas wells and asked a very simple question. How many of them are leaking? Simple question, right? And they categorized all the data into a bar chart. So horizontal axis is how old the well was that they investigated, ranging from brand new wells to wells that were 30 years old. And the vertical axis is the percent of the wells that were affected by sustained casing pressure. In other words, there was gas coming up through one or more of the annuli outside the production casing. In other words, the well had failed. Structural integrity was not there. All right, this could be a graph of my age versus the number of pains that I have. And as you well know, even at birth, sometimes we hurt. But as we get older, we hurt more, because more things go. Same thing, look, young wells fail at the rate of 1 in 20. Young wells, brand new wells, fail at the rate of 1 in 20. Remember that number, 5%. And as wells age, the failure rate goes up, because that cement starts to degrade. There are ground motions that cause the cement to crack. The cement shrinks over time. The casing starts to corrode. The degradation between the casing and the cement goes to hell. The degradation between the cement and the rock goes to hell, and pretty soon more than half of your wells are leaking. And how long are these Marcellus wells supposed to be in existence? Be careful how you answer this question. How long does every Marcellus well continue to have to exist in the state of Pennsylvania? Thank you. Forever on this graph. Okay, so a reasonable expectation is eventually all wells lose their integrity. All right, so I showed this once, and somebody from Halliburton said, "In graph here, you're full of you know what," because this is for offshore wells. This guy's from Halliburton. And I turned to him and I said, "You should know about offshore wells. And you should know about cement jobs in offshore wells. You should know about a cement job on an offshore well called the Macondo, where there was $1 billion investment in that well, and it failed because of a faulty cement job." So let's go onshore. So I dug this data. Again, this is industry data. This is the Society of Petroleum Engineering referee journal paper from 2009. These researchers went and surveyed 347,000 oil and gas wells in Canada. And again, they did the same thing. How many of them are leaking? And they find out that somewhere around 4.5% of them. Older wells are leaking more than younger wells. You can see that here. So remember that, 4.5%, 5%. Earlier this week, I went to the Pennsylvania Department of Environmental Protection and Compliance database, which now is in pretty good shape. It took 4 years for them to get a reasonable, competent, professional database management system so that you, the public, can figure out what's actually going on. And I surveyed, and I asked how many violations were issued in 2011 to all the operators in Pennsylvania for loss of wellbore integrity. Let's go backwards first. Let's go to 2010. In 2010, there were 1,454 wells drilled in the Marcellus in Pennsylvania, and 90 of those wells were cited for wellbore integrity failure, migration of the type I just showed you. That's a 6.2% rate of failure. That number sound familiar? Industry says we're improving all the time. Now, we did tell you we were perfect when we got here, and we weren't. We admit it. We have to learn. My buddy Terry and Gelder at Penn State says it's a really tough industry. They got to learn by actually experimenting in your backyards. So let's go to 2011. There are 1,937 wells drilled. There are 121 well failures. Exactly the same failure rate to within 3 decimal places. Isn't that amazing? So let's see. I conclude that this data is consistent with previous industry data I showed you. In other words, this is a chronic problem the industry has always known about and has never been able to fix for obvious reasons. It's too damn complex to fix it. So what's rare? Rare is 6%. Early, remember, these are wells that were drilled in the year in which the violation was issued. This isn't talking about what are those wells going to be doing 10 years from now, 20 years from now, 30 years from now. So the myth is fluid migration from faulty wells is a rare phenomenon. They'd like you to believe it only happens once in a million times, once in 1,000 times, once in 10,000 times, but there are going to be 100,000 wells in the Marcellus in Pennsylvania. That's what most experts say, in the Marcellus alone. So the truth is that fluid migration from faulty wells is a well-known chronic problem, and there's an expected rate of occurrence. You're going to have 100,000 wells, you're going to have 6% of those wells, 60,000 wells, is that right? 6,000 wells, okay, are going to fail. How many people's well water contamination incidents is that going to cause? And what's the cost to the state? So health impact, there will be contamination. There has been, and there will continue to be contamination of underground sources of drinking water with methane, perhaps drilling fluids, released hydrocarbons, and other things that are down there that are supposed to come up the inside of the well and come out the outside. So, truth, myth, you decide. The most common problem here is not shown.
Okay, let's go back to the start again.
You want to stop there?
Yeah, I think it's gone back to the start. Let's jump back to the start.
Okay, all right, thank you.
Finish.
Thank you.
So yeah, and Graph sort of points out that the industry very much well knows about the chronic problems with well integrity failure, and they've just been trying to cover it and do a propaganda or basically spread mistruths. There's
So what was the date of that video?
What was the date?
Yeah, what was what the lecture that he's given? When?
I think that was 2012.
Thank you.
Where was that? Yeah. One of the problems is steel and cement corrode over time and rust. I was going to show some photos of where I was on holidays, and there was a shipwreck on the side of the beach, in the Ethel shipwreck. And 50 years ago, there was a 600-ton massive steel ship on the beach, and now there's just this tiny skeletal rust that's sort of left over a 50 or 60-year time that it just completely disappears in a saline environment. There's many cattle stations at the moment that are replacing all their water bores with drinking quality water that have completely gone and corroded, and they're having to re-drill, re-bore, add casing, and they're using plastic these days because of the effects that the drinking quality water has on the steel, let alone what is going to happen when you get the salty, deeper underlayers with other corrosive contaminants. One of the chemicals that they often use in the fracking fluid is to try and compensate that is anti-corrosive things like you get in the radiator fluid. That's probably one of the reasons why the frack fluid ponds are so green. It just looks like radiator fluid because it's a chronic problem trying to stop things corroding. And And yeah, it's a bit of a concern when you're thinking they're trying to plug up a well for abandonment, and the steel that they're cementing or plugging into is completely corroded and lost its integrity and calcified, and that's meant to be a strong bond. Yeah, I might move on to my second video here, and this was me yesterday at the back of my air conditioner.
Mr. Trevers, you have 5 minutes left.
Cool.
I'd like to provide a bit more anecdotal evidence of what happens to cement when it is in contact with salt and moisture. Everyone knows steel with cement rusts, so we've got a barrier of steel and a barrier of cement protecting us, or protecting the water aquifers from contamination, which all the hydrocarbons and all the toxins that are actually down in the shale layer. Everyone knows steel rusts. What everyone doesn't know is what happens to cement when it gets exposed. This cement here, I'm about to show you, has been exposed to drinking quality water over a short period of time. So if we open this up, we can actually see the strength and the quality of the cement. Now this is high quality building cement, and the cement that is protecting the vital aspect at the top of the well from what's underneath has been pushed through about 7 kilometres worth of drill holes first and contaminated with hydrocarbons, oils and all sorts of different sort of minerals along the way. So you would expect that the cement at the top of the well isn't anywhere near the quality, and the quantity of salinity and salt and other corrosive materials is high. I mean, that the hydrochloric acid they pump down pure into these wells. It's exposed to extremely high pressures. So one of the barriers is the cement, and the cement is only really at the top of the vertical part of the shaft. The horizontal part of the shaft, the steel tubing sits on the bottom, and the corners as well. So there's no cement protection for most of the shaft, and cement at the top of the shaft is a porous quality, and yeah, it's exposed to all the different sort of salts. I'll show you again a bit over here. This is the powdery sort of effect of what happens to the cement when it gets in contact with a bit of salt and water. And this is to protect us from, or protect the water supplies and escaping hydrocarbons in the atmosphere for eternity. Hello, panel.
Okay,
I'd
yeah.
like to provide a bit more.
Thank you. All right, you've got about 1 minute to conclude, Mr. Trevers.
No worries, thank you. So yeah, I was really disappointed to start seeing these articles here in the thing saying the new territory report showed fracking can be done safely in the Northern Territory and the risk can be mitigated. I'm not sure how regulations are going to stop steel rusting or cement corroding, and yeah, I'm just concerned.
Thank you very much. Thank you. Mr. Trevers, I do want to assure you that this panel has taken the issue of well integrity very, very seriously, for good reason,
Yep.
given its criticality. And indeed, it was for that reason that we engaged CSIRO to do an independent study. Now, I appreciate you take issue with that study, but I do need to, I guess, perhaps just clarify that the figures that we have used in our draft final report, and I'll take an example, let's say, for example, page 71 in section 5.5, come exactly from that CSI report. They do not come from any APIA report, as you, perhaps I misunderstood, have suggested. Now, as I said, you may, hang on a second, you may take issue with the CSIRO analysis and their report, but we have based the figures that we have quoted and we've relied on are taken from the CSIRO report. And if you need any confirmation of that, as I said, you can turn to page 71 of our draft final report. 5.11, and that corresponds with the draft final appendices at page 112.
Yeah.
So just in case there was any misunderstanding, we
No,
have
it's-
taken our data, and as I said, you may disagree with that data, but we have taken our data not from an APA report, but from the CSIRO report.
Yes, you have. But there's a large discrepancy between a lot of peer-reviewed scientific data and evidence that's been here, that the presentations a 50-fold difference between what CSIRO have given and what many people have issued and found clear, relevant scientific data, which is what you put in your interterm of how you will judge and look at evidence. The clear, relevant scientific data hasn't been given any weight, where the CSIRO has been given full, oh yeah, we'll believe you, and we won't actually cross-reference with multitudes of peer-reviewed scientific data and facts, worldwide data, figures. So there's a weight of peer-reviewed data that hasn't been given any weight, really, or any view, and you just, oh, CSIRO, deal with this. It's a sidestep.
That material was before CSIRO, who, in our view, certainly have the expertise and certainly do have the independence. As I said, I accept, and it's an absolutely valid position to take that you disagree with the CSIRO analysis, but I do need to emphasise that we took our data from the CSIRO report, not the APA report. So do you wish to clarify that part of your presentation or retract any part of it?
No, there's definitely no. There's a difference through the APA, but the where they've got it's where CSIRO have gathered their information is in very it's not in alignment with a lot of the world data of 4 million wells that's been ascertained. It seems to me that there's very clear evidence, a matter of fact about well integrity that sort of can be calculated, in the CSIROs where they've gathered their data from is not in alignment. It's very specific and it's very targeted to reach a certain outcome, and it doesn't align with world data studies and peer-reviewed scientific journals and data that I've seen.
There is a sort of a review of well failure rates, including total well failure rates, total barrier failure rates from other jurisdictions in the CSIRO report. You're aware of that, aren't you?
Yeah.
Okay. Well, again, I just want to, it's not unimportant, Mr. Trevers, because you have suggested, and maybe I misheard you, but I had rather heard that you have told us that we have got our data from an APA report. Did I misunderstand you?
You did in the interterm report. The interterm report was
I'm
definitely...
talking about the draft final report.
Yeah. So there was a part where I was talking about the interterm report and my response to it, and I read out part of that. So that was part of my providing evidence and data to the panel about the APA report, and then it flicked over to actually the CSIRO, and that was the differentiation. So I'm sorry if there's any confusion.
So you accept that in the draft final report, we have based our basically we've based our conclusions, and we've taken our data and our percentages from the CSIRO report.
Yes.
Thank you.
So it was, in my opinion, that instead of actually getting to the bottom of the discrepancies yourself and actually analysing the risks, you've actually sidestepped to include the CSIRO, because there was very clear evidence in different reports of literature in the American Department of Environment and other different sort of resources where you could confirm or deconfirm when there's a 1,000-fold discrepancy, but instead CSIRO were brought in, and the panel, as having to assess the risk and report and give back to the public, has sort of sidestepped their responsibility, in my opinion, to deviate the different the deviations or the discrepancies between different...
You don't accept that it was part of the responsibility of the panel to go to experts that are considered to be leading experts in this area and independent experts in this area. You consider that to be an abrogation by the panel of their responsibility?
I considered the panel to be a independent panel, And by
That's not what you said earlier, Mr. Trevers, so which is
yeah,
it?
I no, the panel has been portrayed as an independent panel. When you first came, it was a really strong factor that you presented to the community of being an independent inquiry as different to the Hawke report and other different reports. And then as being an independent inquiry, taking on the responsibility for presenting the facts and getting rid of the myths. When it came to some of those crunch points, by bringing on the CSIRO, you're actually engaged in a Commonwealth government organisation to actually look at a key factor or point, and therefore the integrity of the independence has, in my view, been compromised by giving it off to...
So you don't consider CSIRO to be independent, is that the bottom line?
It's funded by the Commonwealth. It's had $115 million pulled out of its budgets in the last few years, and it is actually being designed to support industry. That's one of its main roles or focus.
Yeah, so Mr. Trevers, you don't consider, I just need a clear answer to this, you don't consider CSIRO to be an independent organisation?
No.
I understand the submission, thank you. Anyone else have any comments? Or we'll start with Dr. Anderson and then we'll come down. Yes, Dr. Anderson?
Yeah, thank you. So I don't work for CSIRO, but I did as a senior scientist for 30 years. So I think I do have some understanding of how the organisation works.
Yeah.
And I just wanted to reassure you that if the CSIRO reported what it did so on the basis of the best available scientific evidence, and it would not have deliberately provided misleading information to the panel. Also note that you referred to another CSIRO study on groundwater in the Amadas, or Greater Teaching Basin, and you accepted those findings, and I would say you were correct in accepting those findings, and if there were errors, they would be genuine technical errors, not politically motivated misleading information. So just wanted to reassure you that.
Thank you.
Yes, Dr. Jones? Right.
With the issue of well barrier failure rates, what Professor Ingraffia failed to mention was that most of those failure rates are actually single barrier failure rates. They're not total failures of well integrity that actually lead to groundwater contamination, and that's a really important distinction. And we did take your initial comments very seriously about this issue of integrity, very seriously. And in fact, that's why we decided we'd get the best expert opinion we could externally to advise us on this matter. And so we went to CSIRO, and indeed their conclusion is that the single barrier failure rate is between 1 and 10%, which is quite consistent with what you were telling us. But that the total well failure rate, which is in other words breaches all barriers and gets out laterally into groundwater, was only about 0.1%. So yes, I think that's been one of our problems, and your problem as well, that certain publications say this, other publications say that. The question is, how do you balance them? And what CSIRO did, they didn't manufacture this information. They actually reviewed the broad base of literature, including the Ingraffia reports and the most recent analysis that has been done, and reached this conclusion, which basically says, yes, single barrier failure is about 1 to 10%, which is consistent. Total barrier failures are much less than that, and they're the ones which can really impact on groundwater quality. So that's what we took away from the advice we were given.
Yeah.
Sorry, did you want to comment on that? Or you don't have to. You looked as if you were about to.
Yeah, one of the big... If you get a single barrier failure, it just opens up an avenue, but it's just a potential for later on, once degradation of steel and cement sort of go, that there's a larger path, like the whole vertical column of steel that sits on the ground. Its integrity is not going to be there.
One of the issues certainly that we do take very seriously, and it's still to a certain extent grappling with, is, okay, you can say the well's maintained well, say to 40 years by the company as they're doing the work, and it's decommissioned, and then you've got a long time after that. What happens then? And that is one of the issues that we asked CSIRO to look at as well as our own research. And the issue is that the conclusion we've come to basically, is that it's very unlikely you'll get vertical fluid migration, but there still is a possibility of methane migration. Now the question is, what are the consequences of that low-level methane migration? Arguably, it could have an impact on fugitive emissions to the atmosphere, which is a greenhouse effect. As far as contaminating groundwater per se, we believe that is a relatively low risk because of the low toxicity of methane. So methane is the most easily measured indicator of issues happening with barrier failures and wellbore integrity. But it is not necessarily a good indicator of toxic groundwater contamination, which a lot of people are very concerned about.
Yeah, but within that, you get the methanes that can come up and actually ignite tap water, like you have seen in different sort of things. If it's coming up in a bore, you get flammable water coming up with a methane sort of things, and benzenes have been noted to sort of be carried along with that migration.
I don't know about benzene being carried with methane, but that's...
Yeah, well...
Yeah, yes, Professor Hart.
Mr. Trevers, you're very, very correct to focus on well integrity. It's a crucial issue, no question at all about that. Dr. Ingraffa's publications and his video, he focused on leakage, primarily hydrocarbons, primarily methane. Yep, there's no question that occurs. The scale of it, we can discuss, but there's no question that does occur, and it's the most likely pathway. And as you pointed out, or he pointed out, and everyone points out, it's mostly the cement rock interface, difficult. But as Dr. Jones pointed out, the other point, yes, certainly that's important, and it's important for greenhouse gases because methane is. But we're also probably more concerned about fluids, fracking fluids, wastewater coming back up there, the 2 to 4 kilometres. And certainly CSIRO's evidence and the other evidence that we've collected suggests that is very, very much less than methane. Are you familiar with that?
Yeah, you're much more likely to get contamination of fluids from the storage ponds and pipelines and all the other different things that can go wrong with man-made sort of things, trucks going through different sort of spills. So yeah, the contamination is more likely to happen to the water surface from above.
We're on the same page there, and we've said so in our draft report. The other point that I just wanted to canvass with you is the question of cement. Are you familiar with the types of cement that the shale gas industry use?
Not 100%, I must be. I know that there's cement, water, and a few additives. You get hardeners, and you can actually delay the setting process. You can have other different sort of chemicals and formalities to actually speed up the process.
Yeah, I think it's a little more than that.
Yeah, okay.
They've got some real challenges. The temperatures, when you get down to 3 to 4K, are at least 150 to 200. That's a hell of a lot more, 200 Celsius, a heck of a lot higher than any of our cements. So there are special formulations. I'd urge you to have a look at some of that. And there are huge number, because the gas industry sees that, as you've pointed out, and Dr. Ingraffa's pointed out, as a crucial component. You know, steel's one thing, cement's another one. So we'd be very interested in anything you're able to discover on that you feel is good or bad, because we recognise that that's a crucial issue for the industry, and of course for us too, in terms of trying to work out the risks that are there. Yeah, I think that's probably all I wanted to say about the cements, without going into detail. Given that you've said this, because what we do is we pick up from people who are critical of various components and so forth, and I think probably we need to look a little bit more. I don't know that we've got that much on the special nature of the cements. We're not apologists for the gas industry, but it's a little bit more than just cement and your home up here. But I think it's probably committing on us to put a bit more down there to give people reassurance if we can.
Especially with these cements, often they're designed specifically for particular corrosive environments. For example, the nature of the groundwater, as you quite rightly point out. If it's exposed to normal cement like this, now I've got a situation like that in my house as well, so I know exactly what you mean by that. But these cements are tested, and in the CSIRO report, they were grappling with this issue of longevity, and they actually found one of the best analogues with the wells that had been put down for carbon capture and storage. We're basically pumping CO2 at high pressure through these systems, and high pressure CO2, and when it mixes with water, is actually a very corrosive environment. So they were drawing on the quite extensive research that's been done on that industry, which is related but not obviously the same as what we're talking about, but it's extremely relevant in terms of the effect of a highly corrosive environment on cement longevity. So they did draw on that work, and that's probably some of the best evidence we've got about how long cement might last, because some of these types of cements, unlike this type of cement, when they're reacted with groundwater or with carbon dioxide, the cement does change, but it actually the crystal structure is actually replaced by another mineral which is actually quite impervious as well. So it doesn't exfoliate like this. It actually it can actually maintain its integrity. So cements ain't cements.
Any further questions? Mr. Trevers, you have come 3 times now and presented to the panel. The panel certainly appreciates you've always put a lot of effort in as well, which is fantastic. You've done your research. You presented us with evidence. That evidence, I can assure you, has been taken seriously and has been examined. We're very appreciative of your engagement with the inquiry, and the panel has welcomed your contribution, and thank you very much.
Thank you.
Thank you.